Okay, so in this video, we're going to be talking about indefinite integrals and the net change theorem. But before we do that, we're going to go actually back into chapter 3, section 9. So chapter 3, section 9 is called Antiderivatives. And I touched upon this concept in the previous video. So now what we're going to do is we're really going to dive into this because we're going to learn just how the derivative and then the integral, which is the antiderivative, are actually related to each other. So let's start off with a really simple example. So let's say we have f of x equals x squared, okay? Well, if we assume that the derivative and the integral are inverse relationships of each other, then what this is telling us then is that there must exist a function, let's call it capital F of x, such that when you take the derivative of this, you're going to get x to the second power. All right? Now, with a function this simple, I think we can use a little bit of intuition and say, well, if I'm thinking about this derivative, first, I know that when I take a derivative, the exponent has to come down in front of the function, and then you subtract the exponent from 1. So if our goal exponent is a 2, then that means the original exponent itself must have been a 3. Likewise, if you look in front of the function right now, let me draw an arrow. Right now, there is a coefficient of a 1, but we know when we take the derivative, we pull the power out in front. So that means this coefficient originally should have been 1/3. Okay, so let me get rid of this 3 out front. All right. So in other words, the original function's derivative must have been 1/3 x to the third. And when you take this derivative, notice you get x to the second power. All right. And what we just found right here, all right, is that antiderivative. Okay? Now, we've been doing this the entire first half of this chapter, in chapter 4. It's just we've been looking at it through a geometrical lens with, finding the area under the curve and drawing the rectangles or using Riemann sums and all that good stuff. Now, what we're going to be doing is I'm going to give you some properties, some rules that we can use to actually find this. But there's a major problem with this, all right? And it's the fact that when we go ahead and we take derivatives of functions, there is one very special derivative property that we have learned. And that property is this one right here, and I'm going to write it. Remember, the derivative of a constant is equal to 0. Because remember, if you were to graph a constant y equals c, you get that nice horizontal line, and the derivative is the slope of the tangent line at any point. So what ends up happening is, and this is the actual way that we're going to be writing out our problems, is what happens is this. If I ask you to find the integral of x to the second dx, all right? What I'm asking you to do is find the antiderivative, okay? But here's what ends up happening. You get 1/3 x to the third, and this is called an arbitrary constant, all right? So this is just some arbitrary constant. It's a random number, okay? And what's actually happening here is this. Even though this is correct, this is what we call an indefinite integral. You have no idea where this integral is starting or where it's going. You know nothing about it. So what ends up happening is when you have indefinite integrals, you will get a family of solutions. Okay. So for example here, and I'm going to pull out Desmos here for us. All right, and the reason being is 1/3. I'm just going to plot 1/3 x to the third real quick. All right, is notice that if you, let's say you have 1/3 x to the third plus 5. If you took that derivative, you still get x squared. If you did the same exact thing, but instead of using plus 5, let's say you used -9, you still get, let me zoom out, you will still get the same exact derivative, all right? Even if you did 1/3, plus 0. Notice when you take that derivative of 1/3 x to the third plus 0, you still get the same exact derivative. So the problem, like I said, is when we are talking about indefinite integrals, you end up getting this arbitrary constant, okay? So just be aware of that. There's a difference between a definite integral, meaning it has the limits of integration, and then an indefinite integral, which is what we have in front of us here, where there is an family of solutions, or integral curves, or integral solutions is another way to say it. Now, what's really interesting about this, and we tend to get lazy a little bit in Calc 1, all right? Because we don't want to overload you with too much theory or anything like that. But what I just wrote right here, and I'm going to write it again, the integral of x to the second dx. Technically, this is going to be equal to dy dx, which is a derivative, which really means we are integrating both sides, all right? And when you integrate both sides, on the left-hand side, you end up getting y. And on the right-hand side, you get this 1/3 x to the third plus c. We call this, actually, hold on, let me be more specific here. We will call this a differential equation because it contains a derivative. The most famous one you've probably heard of is F equals ma, which is Newton's second law of motion, which can be rewritten as F equals the second derivative with respect to time of displacement. So there is your first real introduction into differential equations, where this right here is a second order constant coefficient linear homogeneous differential equation. Big words for really easy way to solve it, to be honest. See me in math like 251 if you want to learn how to solve a problem like this. All right. But anyways, so what I want to do now is just kind of go through and give you the formulas for all this. In fact, in every calc book, at the very end of the calc book, you will just see a whole table of just integrals that have already been solved. 99% of the time, we're going to be able to do them by hand, but I might throw a couple in where it's like you just got to look them up and just, give me the answer. All right. So give me a second here. I'm going to copy and paste this into our notes. All right. So here are just the first 20 basic forms. Now, I uploaded this reference card a couple weeks ago. So if you're not familiar where it is, I'm going to show you right now. All right, so here's our notes. And the ones that I really want us to be responsible for, and I'm going to highlight them here for us. All right, is definitely going to be this one right here. So here's our first one. Okay, and this is the power rule. All right, so whenever you have a function of u, or better yet, a function of x raised to an exponent, notice what you do is you will take the exponent, add 1 to it, and then divide by the same exact number. So if I just scroll up here a little bit and we look at what we have right here, notice that the integral of x squared dx is going to equal, add 1 to the exponent, and then divide by the same thing, and add an arbitrary constant, which gives you 1/3 x to the third plus c. So there is our nice little shortcut. Otherwise, we would have to use the Riemann sum thing, where if you remember in the previous section here, all right, if I can find it real fast, right here is where we use the Riemann sums, and where is my, there it is right there. There's the Riemann summation formation for I to the third power. Now we could just use this simple integral rule for us that we just learned. So these rules are going to help us out tremendously. All right, but you're responsible for rule number 2. All right, you will be responsible for the 6 basic trig rules, and they will be straightforward. Okay, where is, I'm looking for the integral of a constant, but I don't see it here. They probably got it hidden somewhere. All right, no worries. So the integral of a constant times dx is going to equal cx plus another constant k. All right, so you will be responsible for that. I think your book should have like a nice little table. In fact, I'm going to pause the video here and just see if I can find like a little nice comprehensive table that I can just copy and paste into our notes. So just give me 1 second here. All right, so I did find us a nice little table here under our text, and it's table 1. In this section, it's at the bottom of the page. And notice from here, I'm just going to go down the list and kind of explain what each one of these do. And what I can also do is provide you with a very short little example of each. And then what we're going to do is just dive right in and just do a bunch of problems. Okay? So the very first one, what it says is you have the integral of a constant times a function of x times dx. Now, what this rule says is that you can take the constant and pull it out front. And then all you have to do is integrate this constant, integrate the function of x, and then put the constant out front. So an example of something like this would be like the integral of 3x to the second dx. So first thing I could do is take the constant and pull it out front. Oops, sorry. And now I can focus just using my power rule and integrate x squared dx, which is going to give me 3 times. Now I'm going to integrate x squared dx. So it's going to be x to the third over 3 plus some arbitrary constant. Now when I distribute the 3, I'm going to get x to the third plus k, where k equals 3c. Now, normally, all we would really write here for our final answer would just be like x to the third plus c, because a constant times a constant is another constant. And if you go back and you were to differentiate this, all right, to check ourselves, so if you were to differentiate the check, notice that I don't care what that constant is, because no matter what, when you differentiate this, you're going to get 3x squared, and the derivative of a constant is 0, which is the original function that we wanted to integrate. So just be aware that some books will just put plus c, versus the higher you go up in math, like in a differential equation book, they will definitely say where k equals 3c, because differential equations, once you start getting more involved, they kind of start to behave a little bit differently, especially when you're talking about particular solutions versus complementary solutions and things like that, which probably made no sense what I just said, but that's okay. All right, so let's keep moving. The next rule is going to be the integral of a constant times dx, and this is going to equal kx plus c. All right, so an example of this would be something like the integral of, actually, let's use a different constant here. We'll use pi dx. Now, pi is a constant. You got to remember that. So according to this rule, all we have to do is take pi times x and add the constant there. All right. So the way that we kind of think about this, all right, and I'm not going to go into like a big proof of this, all right, but the way to kind of think about this would be, this could be like the integral of pi times x to the 0. Now we know x to the 0 is 1, all right, but to keep this like in a simplistic idea, notice that if we wanted to, we can pull the pi out front. And then according to our power rule, once again, we're going to add 1 to the exponent. Oops, sorry. We're going to add 1 to the exponent and divide by that. So it would be x to the first over 1 plus c. Which gives me this pi x plus a constant again. So that's really what's happening here. All right, but like I said, I don't want to get too involved in it, because then you're like looking at a proof and everything, and it's a lot more involved. All right. If you're really interested, I can write it up for you, but I'll just do that on the side. I'm not going to put that in a video here. I want to keep this video relatively short compared to the hour-long videos I've been giving. All right, let's keep moving. So the next couple ones are actually really simple. All right. The integral of sine x dx equals negative cosine x plus c. That is the example right there. I mean, there's nothing more I can do with that. Okay. When we get into the next section is where I can provide you with more examples, because we're going to be using a technique called use substitution. So with these next trig ones, I'm just going to write them out. You're just going to be able to recognize that when you have the integral of secant squared x dx, that is going to equal tangent x plus a constant. The integral of secant x tangent x dx is equal to secant squared x. I'm sorry, just secant x, not secant squared, but secant x. The integral of cosine is equal to sine plus an arbitrary constant. The integral of cosecant squared x is equal to negative cotangent. And finally, the integral of cosecant x cotangent x dx, let me put these in parentheses, is going to equal negative cosecant x plus c. And the most important one that we're going to be looking at, put a big star next to this, because this is one we're going to try to use as much as we can, is our power rule. So we have the integral of x to the n dx. That is going to be equivalent to x to the n plus 1 over n plus 1 plus an arbitrary constant. And there's only one exception. N is not allowed to equal 1. That ends up being the natural log. Okay? All right, so this is where I think you should at least take some time, familiarize yourself with these formulas that we just went over, okay? Maybe put them down on a note card or something like that, like get to know these formulas. Oh, I did forget to explain this last one here. All this last one right here says that if you have the integral of two different functions, you can distribute the integral to each one of those functions, and it doesn't matter if you're adding or subtracting. That's all that one says. Sorry about that. But anyways, what you should do, all right, is note cards on the front of the note card. You know, have like the integral of sine x dx on the back of the note card, negative cosine x plus c. Rarely do you ever hear me say memorize this. This is something you want to at least not necessarily memorize, but definitely familiarize yourself with it. And once you kind of feel comfortable after you wrote them down or anything on a separate sheet of paper, nice and neat, so you have them readily available to your left or right as you're doing your work, all right? That's when you should come back to this video, because I am just going to do a bunch of examples here. So here's our first example. We're going to integrate the 4th root of x to the 5th dx. Now, just like in derivatives, you gotta sometimes algebraically manipulate what you got to get it into a form that you can use for one of your properties. So what we're gonna have to do here first is we're gonna have to rewrite this as x to the 5/4 power. And then when we integrate, remember, we're gonna add 1. We're gonna add 1 to the exponent. Now remember, 4/4 is still 1. And we're gonna divide by that. We're going to add our arbitrary constant, and then we're just going to simplify real quick. So this is going to equal x to the 9/4 over 9/4 plus c, and then write it as 4/9 x to the 9/4 plus c, because you are dividing fractions. All right? For the next example, let's do the integral of 5 plus 2/3 x squared plus 3/4 x to the 3rd dx. Now, going from left to right, you can see, actually, you know what? I'm going to write this one out. Normally I wouldn't, normally I don't do this, but I'm going to write this one out. We're going to integrate each one of these by distributing the integral sign, which you're totally allowed to do. Oops, sorry. And this just goes to show you, like, everything that you can do with this. So there's me distributing the dx in the integral symbol. Now going from left to right, the integral of 5 dx stays the same. This 2/3, I can move that out front of the integral. That way I can focus on the function of x. And I will do the same thing with the x to the 3rd power dx. And then finally, going from left to right, I'll integrate. I'm gonna need the constant rule for this, so that's gonna be 5x plus, this will be 2/3 multiplied by x to the 3rd over 3. This will be 3/4 times x to the 4th over 4. Add your arbitrary constant in. And just to kind of clean this up, you get 5x equals, oops, sorry, not 5x equals, 5x plus 2/9 x to the 3rd plus 3/16 x to the 4th plus our little arbitrary constant c. Now remember, I said earlier that this is a differential equation, which means technically there's a y out front here. And if you wanted to check yourself to make sure you're correct, if you were to take your answer and differentiate it, you should get the original function that we were trying to find the antiderivative from. So if I just went ahead and did that real fast, and I'll do it in red directly underneath just so you can see it. Y prime is going to equal the derivative of 5. X is 5 plus, and I'll write it out first. We're going to get 3 times 2/9 x squared plus 4 times 3/16 x to the 3rd. Derivative of a constant is 0. And then if I simplify going from left to right, I'm going to get 5 plus 3/9 turns into 1/3, so it's going to be 2/3 x squared. And then 4/16 is 1/4, so that's going to be 3 times 1/4, which is 3/4 x to the 3rd. So notice you get the same exact function. So, math is one of those beautiful subjects where you can literally take that test or do the homework, and you'll know just by checking your answers how well you did or not. But let's just keep moving on. Let's just keep moving on here. All right, let's try this one here. All right, we're going to do the integral of 1 plus the square root of x plus x, all divided by the square root of x dx. So once again, this is a situation where you're going to want to simplify first, because notice we don't have any rules that really deal with fractions. I mean, in fact, in Calc 2, you're going to learn about trigonometric substitution. You're going to learn about partial fraction decomposition, and that is where we apply those techniques. But here, because we have a monomial, actually not even a monomial, just because we have one term in a denominator, just separate it. So we're going to get the integral of 1 over the square root of x plus 1 plus x over the square root of x dx. Now, to simplify this a little bit further, we're going to get x to the negative 1/2 plus 1 plus x to the positive 1/2. Okay? And then when we go ahead and we integrate this, and I'm just going to do it from left to right, we get 2x to the 1/2 power plus x plus 2/3 x to the 3/2 plus c. And if you type this in the WebAssign and it marks it incorrect, then you might want to type it in using the actual square root notation, I guess. Meaning, take that 1/2 and write it as a square root. I don't know why it would, but this semester, if it's one thing that we've definitely learned, it's that WebAssign is definitely a very finicky beast, and sometimes the hardest part about it is just knowing how to type in an answer. That's why, I've been saying this all semester, I always look over the quizzes and tests just to make sure that there's no typos or anything like that, because I don't want to see anybody get something marked wrong that they should have gotten right. All right, now, the next couple examples would be, this is where students tend to start running into some issues. And it's not because you don't know what you're doing. It's because it's been a while since you had to use like your basic trigonometric identities and everything like that. All right. So we just got to be careful. All right. Now, if we look at the integral of 2 plus tangent squared theta d theta, all right, here's the problem. And hopefully, I don't even know, do I still have it copy and pasted? Yeah, there we go. So notice in our little rules, all right, especially like down here and down here, notice there's no tangent squared theta, all right? So the question now becomes, well, can you still integrate tangent squared theta? And the answer to that question is absolutely. What you need to be able to do, though, is think about all those trigonometric identities that we learned a long time ago. So if we go back into, where is my note card? All right, and what we're going to do is I'm just going to rewrite the problem. All right, now directly underneath, 1 plus tangent squared theta equals secant squared theta. And then if I just subtract 1 from both sides, I get tangent squared theta equals secant squared theta minus 1. And I'm going to take this and make a substitution, because if you look above in our table, I know what the derivative of secant x dx is, or secant squared theta d theta. It's tangent theta. So this is, like I said, this is where if we run into issues, this is where it's going to be. And it's just because you got to familiarize yourself with just rewriting these things. So we're going to get the integral of 2 plus. Anytime you make a substitution, put it in parentheses. Now, going from left to right, we'll just distribute our integral sign. There we go. And directly underneath, we're going to go ahead and just write the answer. So we got the integral of 2, which is 2 theta, plus the integral of secant squared theta, d theta, which we know to be tangent theta, minus the integral of 1 d theta is theta, plus a constant. And I didn't even see this when I was doing this, but those are like terms right there. So you can group them together. So we're going to get theta, it's a horrible looking theta, plus tangent theta plus c. All right. So like I said, if we run into issues, this is where it's going to be. We got to be careful with this. Let's try another one here. We're going to integrate secant t times a quantity, secant t plus tangent t dt. So the first thing I'm going to do here is algebraically manipulate a little bit. We're going to get the integral of secant squared t plus secant squared tangent, or I'm sorry, secant t tangent t dt. And once again, if I could just pull out our little table right here, notice right here is the integral for secant squared. Right here is the integral for secant x tangent x. So we have what we need. So bottom left hand corner of your screen, I'm just going to write the integral of secant t, or secant squared t, is going to be tangent t plus, and then secant t tangent t is going to be secant t plus a constant. All right. So like I said, it's just a matter of just kind of slowing down and looking and seeing and saying to yourself, right, is there a way that I can algebraically like manipulate this to make it look a little bit easier for me? Notice that I really didn't do a lot with your basic functions of x, like up above, like, and what I mean by that is like these examples right here, these two examples. This was just all about manipulating it so you can make a power. That's pretty self-explanatory. You get better at it with practice. The examples I really like to hammer on are the trigonometric ones, because those are the ones where I will get 15 questions, and it's, you know, and they're all great questions. It's just, it's been a while since you've done something like that. So I always like to show the more trig ones. So let's do a couple more trig ones. So we got the integral of 1 minus sine cubed t over sine squared t dt. All right, so I hope you can see where this is going. First thing I'm going to do is separate these terms, because I have one term in my denominator. So I'm going to make it 1 over sine squared t minus sine cubed t over sine squared t dt. Next, I'm going to simplify a little bit further. 1 over sine squared t is going to be cosecant squared t minus sine t, put this in parentheses, dt. And then finally, if I can pull out my table again, where is it? Right here is cosecant squared t. And then right here is cosine. So we just need to be careful about how we write this. So now that we're going to integrate, cosecant squared t turns out to be negative cotangent t. Now you do have a minus sign, so we're going to write minus. Now we're going to integrate sine, which is negative cosine, plus some arbitrary constant. And just to clean this up, we have a double negative, so we're going to make it negative cotangent t plus cosine of t plus a constant. All right, so the only extension that I can do here with us is now we're going to go, I guess, back in time a little bit. And we're going to integrate from 0 to 12, x minus 12 sine of x dx. So although our rules above are for indefinite integrals, they still apply for definite integrals as well. And remember, what I have in front of us right here is a definite integral because I know I'm going from 0 to 12. So what I want to do first is let's just go ahead and let's find what this integral is, all right? And then let's understand what's happening. So first thing I'm going to do is I'm going to go ahead and distribute my integral sign just so you can see how all this is going to work out. So we get the integral from 0 to 12 of x dx minus the integral from 0 to 12 of 12 sine x dx. Now I'm going to take this 12 and pull it out front. So we're going to get the integral from 0 to 12 of x dx minus 12 times the integral of sine x dx from 0 to 12. And what I'm going to do first is we're going to integrate this. So when we integrate x to the first power, we're going to get 1/2 x to the second. And there are ways to write this, but normally we just write it like this. We put a big bracket on the right-hand side, and we put the lower limit down below and the upper limit above. Let me write that a little nicer. Here we go. All right. And what we do here is when we're evaluating definite integrals, it is always going to be the upper bound or the upper limit subtracted our lower limit. So what I'm going to do here is I'm going to put it in brackets. I'm a big fan of putting things in parentheses first and then making my substitutions. So in this first upper limit, we're going to let x equal 12. So I put a 12 here. And then in the second one, I let x equal 12 again. Oh, sorry, not 12. In the second one, we're going to let x equal 0. So put a 0 there. All right. And all you would have to do here is just take 12 squared, which is going to be 144. And then 144 divided by 2. This is going to equal 72. So for this first part, we get 72 minus, and we do the same exact thing for the integral of sine x dx. All right. So let's go ahead. Let's do that. So I'm going to put a 12 out front. We know we're going to multiply by 12. I'm going to zoom out here a little bit. So we get the integral from 0 to 12 of sine x dx. Now we know the integral of sine is going to be negative cosine and evaluate this between 0 and 12. So we get negative cosine of 12 minus negative cosine of 0. This is going to be, oops, don't know what happened there. Where'd that thing come from? So this gives me negative cosine of 12 plus 1. All right. Now, the thing you got to remember here is we need to take this and substitute it all the way back up here. So at the end of the day, here's what you get. 72 minus 12 cosine of 12 minus 12, which reduces down into 60 plus 12 cosine of 12. All right, so this is, remember, this is an exact answer. But if we wanted to, we can take this one step further. And we can say, well, this is approximately 70.1262 in terms of area underneath the curve. All right? Now, what we got to be careful of is this. This number does not represent the total area under the curve. This area represents the net area under the curve. So let me show you what I mean here by grabbing Desmos again. And I'm just going to go ahead and I'm going to type in our function. So it's going to be x minus 12 sine x. All right. And then what we're really interested in here is we wanted to go from x equals 0 to x equals 12. All right, and give me 1 second. I'm going to clean this up and make it look a lot nicer for us. Let's get rid of those minor grid lines, and we're going to really tighten this up. So we're going from 0 to 12. And I'm going to zoom out just a little bit. There we go. Just like that. And let's fix this. So this is red so you can really see it. And we'll make them dotted lines. All right. That is good enough for me. So copy and paste this into our notes. Perfect. All right, so. Oh, that didn't. What happened? It switched on me. I'm really sorry. Let me do this again. That's what I wanted. All right, much better. So here's what's happening here. All right. We wanted to find the area underneath the curve, and this is our function, f of x equals or this is the integral of x minus 12 sine x dx. All right, so here's what's happening. We were finding the area under the curve, which means this area here, this area here, this little area here, and finally that area right there. But if you notice, going from left to right, this is below the x-axis, this is above the x-axis, this is below the x-axis, and this is above the x-axis. So what's actually happening here is when we integrate from 0 to 12, x minus 12 sine of x dx, what's really happening is this is giving us our net area from 0 to 12, which means we're adding these two areas together here. So I'll highlight them in green as best I can. So we're adding these two areas, and at the same time, we are subtracting away the areas underneath the curve. So remember, whenever you are using these formulas, they give you net area. If you want total area, then what we would have to do here if you wanted total area, what we would have to do is find the area in this region, region 1, and we would take the absolute value of that. Then you'd have to find the area here in region 2, and you would do that for every single one of these regions. And then you would add, the total area would equal region 1 plus 2 plus 3 plus 4. So please make sure you are aware of that, because sometimes you may do a problem and you're integrating between two bounds and you get an area of 0, which doesn't make sense, all right? Especially when you graph it. And what's happening is you're getting an area of 0, which means your areas are canceling themselves out. So what you could do there is just find the area of 1 and double it, which is a really intuitive approach to it. Okay, so I'm going to do just one more example, all right? But I'm not going to really draw this one out here. What I'm going to do, we're just going to go right into it, all right? So we're going to integrate from 0 to 3, 1 plus 6w squared minus 10w to the 4th dw. Now going from left to right, we're just going to integrate. So the integral of 1 would be w, plus the integral of 6w squared would be 6 over 3 w to the 3rd, minus the integral of 10w to the 4th is 10 over 5 w to the 5th. And we need to evaluate this between 0 and 3. However, before we evaluate between 0 and 3, let's clean this up a little bit. So we get a w plus 2w to the 3rd minus 2w to the 5th. And finally, we can evaluate between 0 and 3. So the way that I'm going to do this here, I'm just going to write out two big brackets. Underneath, I'll write upper, lower, and I'm just going to go ahead, like I said, put my parentheses in first, because I'm old school like that. And then substitute a 3 in. And finally, for my lower, I'll do the same thing, put my parentheses in first. And then substitute in my lower bound there. All right, and then finally, all we have to do from left to right is just simplify. So we're going to get 3 plus 54 minus 486 minus 0, which equals negative 429. And this just means the area lies beneath the x-axis. So I don't want to confuse you. I'm going to show you what I'm talking about here when I said the area is like beneath the x-axis.